So today we are going to learn something called meter bridge. So before we learn any device, we need to know on what principle the device works or is based on, because sometimes this may be a question itself that a particular device works on this principle or that principle. So you will be asked to answer that as well. So meter bridge is a device which works on the balanced Wheatstone bridge, and the concept of balanced. So it is a device which is used to find the unknown resistance and is based on the balanced Wheatstone bridge condition. Okay. So it is based on balanced Wheatstone bridge condition. So first of all, we'll try to also learn something about the balanced Wheatstone bridge. So have I discussed this before in capacitor or in current?
Yes.
Okay. So Wheatstone is basically a network of 5 branches. So we have 5 branch, and let's represent each branch with some resistance R1, R2, R3, and R4. Then we have a bridge element. And this bridge element will have a galvanometer. And of course, you can represent some resistance. And then we will have some power supply, which is orthogonal to the bridge element. So such arrangement is called Wheatstone bridge. And a balanced condition refers to the null current or null deflection through galvanometer. So when you don't see any deflection through galvanometer, you tend to say balanced condition. So if I call this current as IG, in balanced condition, the current through galvanometer must be 0. So we can also call this as null deflection. So in balanced condition, this IG must be 0. And therefore, whatever current you may assume through the cell, the current will divide at this junction. And because IG is 0, so no distribution of current will take place at this junction as well as at this junction. So the same current I1 will go through here, and the same current I2 will go through here. So if you look carefully, the bridge element is not participating in offering any resistance to the circuit. So from left side, we have two resistance R1, R3. And from right side, we have two resistance R2 and R4. A similar current which is getting divided on the left, and if it is arriving in a similar fashion on the right, that is only possible when the resistance are in the same ratio. Because we know that current division, and we have studied something called current divider rule. And we have seen that the division of current depends on the ratio of resistance. It doesn't depend on the actual value, rather the ratio. So if I1, I2 is the division on the left, and if you look from the right, it is a similar division. It means the ratio is bound to be similar. So R1 is to R3 must be equals to R2 is to R4. And if this ratio is maintained from both these sides, then this condition can be achieved, which we can prove mathematically as well without any difficulty. So if I call this potential as A, let's call this potential as V. And if I call this potential as 0, so it is representing the same cell. And if I call this potential as V dash, then this must be V dash also, correct? Because there is no current through the galvanometer, which means the entire branch will have 0 potential difference. And therefore, on the left, you can add a V minus V dash. You can add as I1 R1, or you can write I2 R3. Is this part clear? How I am writing?
Yes.
And not only that, you can, V minus V dash, you can also write on the right hand side. No. V dash minus 0. You can write on the right hand side. And how you can write? V dash minus 0 we can write as
I1 R2 is equal to I2 R4.
And now you can take the ratio, right? 1 divided by 2. The moment you take the ratio, the current will get cancelled out. So whether current will flow through the bridge element or not, it is predetermined using the ratio. So if resistance will follow the same ratio, you will never face the redistribution of current. So current from the top branch will flow continuously. Although you can see the top branch is having resistance R1 and R2, and the bottom is having resistance R3 and R4. It's still there is no redistribution. So if the ratio is maintained, and this ratio can be written in multiple ways. So this ratio we can write in multiple ways, and how we can write? So R1 by R3 is R2 by R4. So you can take this ratio, you can take this ratio. If it is same, again it's a balanced. You can take this ratio, you can take this ratio. If it is same, again balanced Wheatstone bridge. And the third way of writing, you can say third form of writing is if you take the cross product, so R1 R4, or you can say R1 R4 is R2 R3. So if the cross product of resistance, if the values are same, then it is again the balanced Wheatstone bridge. What really matters is the ratio. Okay. The ratio is better way of understanding. Cross product is consequence of the same. So the balance condition can be determined in 3 possible ways. You just check the ratio of resistance connected to the same node. So R1 by R3, if it is equals to R2 by R4, then it is balanced and nothing will go through the bridge element. Or if R1 is to R2 is same as R3 is to R4, again it's a similar situation. So this is the balance condition, and you will get many questions based on balanced gravitational bridge in JEE Advanced particularly. And the moment you see a very complex question in JEE Advanced, what should click to your mind is that it is based on balanced gravitational bridge somewhere. So somewhere in the circuit you can reduce it. So let's say if I draw a circuit like this, and no one will tell you that this is balanced or not. So and then if I ask you what is the current through this circuit, I is how much? So if you look carefully, although I have
Upper one is
highlighted,
balanced with
yeah. So which resistor we can throw out?
3 middle.
Correct. So it will not be, highlighted the way I have drawn. So in examination, you have to search for it. That's why such questions at first looks difficult, but it's very easy. So once you remove it, it's a simple parallel and series combination of a resistor, which I hope that you can simplify or reduce, and you can find the current. Can you find the current now?
Yeah.
Do it, everyone.
Excuse me, sir.
Yes.
Is R equivalent 95 by 29?
R equivalent. Okay, I need to check them because that's a really bad value. I can see.
Yeah.
So it is 6 and 18, right? So
Yes.
18 by 4, 9 by 2. 9 by 2 is there so far.
Yes.
And plus 1 plus 1 plus 5 plus 3, right?
Yes,
Yeah.
I got the same.
9,
Same.
10. 29 by 2, right?
Yeah.
Yes.
So 18 by 29 by 2.
29 by 2. 36
So
by 2.
36 by 29.
Okay,
36.
I actually skipped 5. Okay, got it.
Yeah. So is this clear to everyone?
Yes.
Yes.
Not very difficult. So the idea is you have to understand that which eastern bridge will come in multiple facets. So you need to just identify actually. And if the question is appearing really difficult, the simple trick is it is based on Wheatstone bridge in JEE Advanced. So in JEE Advanced, the toughest question is question based on Wheatstone bridge. Okay. So there are some other forms of Wheatstone bridge which is not very uh, you can say appealing in this shape. So let me show you. So it's good to know. Find the R equivalent between N. Do this.
So 2R.
Yeah, I think 2 or R maybe. R, I think. Yeah, 2 R. 2 R is the right answer. Correct.
Sir, even I got 2R.
Very good. So you
Sir,
can see
but,
the middle 2 R is the bridge element, right?
Yeah.
yes. Sir.
You just need to redraw in this format. And This you can throw away. Okay, I say OLX, and the rest is simple, right? So
Yes, 2R.
this is 2R. Correct. So as I said, sometime it will be obvious, sometime it will not be obvious. But if you put some effort, you will be able to see that Wheatstone Bridge somewhere. Because the JEE syllabus is not difficult. So if you see something difficult, think about it. Now this question is not from JEE. This question is from one of the old KVPY question, which is nowadays obsolete. So this examination has been scrapped by the government.
Yes.
But nevertheless, that question will be still live. So it's a very famous question. So we have a square of 1 ohm each. So every side represents 1 ohm. So you can say it's a uniform wire of resistance 1 ohm. And the length of each wire is 1 meter as well. 1 meter. So 1 ohm, 1 meter. Just name it A, B, C, and D. Now there is a resistor of resistance 1 ohm. So it's not a wire, it's a resistance of 1 ohm value, which is randomly connected to a point D. Okay. Randomly connected to the point D. And no, that's it. Sorry, this is E. D already used. And now we connect some cell across B and E, and the distance is X. Now 1 meter is 1 ohm, so X meter will be X ohm. So that's also true, right? Now, if a source of a potential difference or battery or voltage source is connected across point B and E, such that if potential of A is same as potential of C, then find X. Questions clear?
What is X? I didn't get.
X is the distance,
Okay.
the length of the wire.
Okay.
So at which point you must connect the E so that potential of A and potential of C becomes equal. So try for a while and then I'll solve. It's very interesting. Think about the Wheatstone bridge from the basic, that the A and C is basically the bridge element end, right? Although there is no bridge element shown, but A and C will act as the bridge element kind, isn't it?
Yes.
And the
Yeah.
potential of A and C will be
Yes.
equal only when you know when it is equal. So try this. This is sufficient hint given. I think enough time I have given. So when you look from the terminal end, now here E and B are the terminal. The ratio of the resistance on the two sides must be same, yes or no?
Yes.
So from the B side, what is the ratio of resistance? 1:1. This is 1, this is 1. So from B side, the ratio of resistance is 1:1. Correct?
Yes.
But if you look from the E side, this entire term is single resistance and this is single resistance, right?
Yeah.
Yes.
And if you realize that this entire resistance is how much? It is 1 plus x into 1 upon 2 plus x.
Yes.
Upon the other one, which is 1 minus x. Because here the length and resistance are proportional, right? That's it. Is it difficult to solve? So what I did, what I wrote is RAE upon R to E to C is same as RAB upon RBC. Because that is the only condition when A and C will have same potential. Because this is a direct question of balanced Wheatstone bridge condition, where the bridge element is missing, it is not present. How many of you are able to realize this?
Yes.
So how many of you are not able to realize this?
Sir, can you explain?
So I did not get it.
Okay. So if you are at E, then resistance will divide on this side and this side.
Yes.
Correct. So from here to the C point, what is the resistance here?
1 minus 6.
1 minus x.
And from E to A, how much resistance? These are in
One.
series and parallel.
Yes.
So we have to reduce this into single resistance. No?
Mm-hmm.
Yeah. Okay.
Once you reduce it, you will get this much.
Yeah.
Okay. So
Yes.
this upon this must be same as this upon this. Then only A and C will have the zero current or zero like same potential. Okay.
Yes.
Now solve it. Tell me the answer. So x square plus 2x plus x 3x. Maybe you can just check if I missed something. So this x turns out to be how much? Oh, something is wrong. Something is
Sir, I
wrong.
think your equation is wrong.
Yeah,
It
it
is
is.
minus
It is.
minus 1 x square plus 2x minus.
Yeah, I think 1x. Oh, okay, okay. That's why. It is x plus 2. I have written wrongly here. Correct, correct,
I think answer is minus 1 plus root 2.
correct, correct. That's right answer. So answer is root 2 minus 1, which is 0.732. No, oh, sorry, 414. So it is, and this is a fraction, right? It should have been fraction because the total length is 1 meter. So this is root 2 minus 1. This was KVPY question, and I think this was the toughest question from the balanced Wheatstone bridge. So what you need to look is the ratio actually And in various JEE problem also, if they ask you how the current will distribute and all, always try to analyze through the lens of balanced Wheat-Easton bridge. Try to check for the criteria or condition. Now there are some unseen situation where the balanced Wheat-Easton bridge is applicable, but it's not so obvious. So far I have shown you just 4 resistance or 5 resistance, but we may have a situation like this. So if I make it 1, 2, 3, 4, 5, and if I make this as 2, 4, 6, 8, 10, and if I call this as 1 ohm, 1 ohm each, now definitely at first go this doesn't look like a balanced Wheat-Easton bridge, but
Yeah.
it
Although
is
1
actually,
ohms will manage.
yeah.
Yes.
So if you look at the topmost point, I mean topmost resistor and the bottommost resistor, they're in the same ratio. They're growing, but in the same ratio.
Yeah.
So when the ratio remains same, then the middle branch will have no current. So you can basically throw out all of these.
Yes.
So this is something which is like a application of balanced Wheat-Easton bridge, but not very obvious. And once you throw out, it's a very simple question, right?
Yeah.
So just throw it. Why we are throwing? Because the ratio is maintained on both sides. So 1, 2, 3, 4, 1, 2, 3. Yeah. So I hope you can solve this 1, 2, 5, 1, 6, 8. So the top will be 5, 4, 9, 3, 12,
Answer
3,
is 10,
15,
I think.
15, and bottom is how much?
30.
30. So 15 and
Yes.
30 is 30 by
parallel.
3.
Yes. 10.
Correct. That's the right answer. So is this clear so far, everyone?
Yes.
Yes.
So we are done with the balanced Wheat-Easton bridge. Sometime you will get even more complex, that you will get branch or branch and branch. So let's say if I create something like this, at first go it will not look as again as a balanced Wheat-Easton bridge, but it will be. And then you have some branch here. And within this branch, we have some complex circuit. So this is called the black box model. So it is a circuit of circuit. So every branch itself is a circuit. So you don't know what is inside. 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 But whatever is inside will have some net value. Correct?
Yes.
So using that net value, you have to simplify or you have to check for the balanced Wheat-Easton bridge condition. So just be open with a variety of situation that you are going to face. And JEE is always tricky, not difficult, but always tricky. So you have to figure it out that, okay, this situation may arise. And they may, sometimes they will draw the diagram in such a way that it will never look like a Wheat-Easton bridge. So this nice diagram you won't get. So you have to convert something not so nice into nice. So the moment you see it's a not parallel series combination question, think about mirror symmetry, think about Wheatstone bridge, think about short circuiting, think about redrawing the circuit, think about the iso potential points. So these are the alternatives that we go through the moment we see the question is not reducible at first go. And in worst case scenario, what we do? So in the worst case scenario, we apply the delta star.
Yes.
So when we see no hope, then we call star, the star method, delta star. Okay, so now this was the Wheatstone bridge, but what we are going to learn is a device called meter bridge. So this device is mounted on a table. So this is a metal strip which is mounted, or you can say fitted on a wooden desk or table, and a resistance in the form of a wire is connected from here to here. And the length of this wire is exactly 1 meter. And that is why it is called meter bridge. Okay, so now I know why the name. And as I said in the last lecture, that when you learn some instrument, you need to know all the details, the way it is said. So there is something well defined, you can say conventional thing, which we need to follow. So you can see there is an empty space on the left and there is an empty space on the right. So these are called gaps in which you connect some resistor. So this is called left gap for the obvious reason. This is called right gap. And towards the left gap, we take 0. And towards the right gap, we take 100. When you connect a source of energy or a battery, and the positive terminal of the battery must be connected on the left gap. So now these are like, oh, this is too big. Let me get simple. And we put a meter scale across the wire so that you can read the jockey position. And of course, there is a calibration. Okay. So this is your ruler in which you can read from 0 to 100 value. And the wire which we connect, yeah, this is called the resistance wire. So these names are very much conventional. And you can assume some value, let's say R naught ohm is the resistance of this resistance wire. On the left gap, we connect the unknown. So again, you need to remember that unknown resistance is connected on the left gap. And the right is called the known or standard. And that is why we use the symbol S for the known or standard. And then we need to have a slider, a jockey. So this slider will oscillate or slide over this wire till we get the null deflection. And then C is called null point. So first of all, we define something called a resistance gradient. Let's call K. So K will be R naught is the resistance. Length I'll keep in centimeter itself. So we call ohm per centimeter. So this is the resistance gradient. So if I call this distance as X, this will become 100 minus X.
100 minus.
So if the resistance, if we wish to write the resistance of this length OC, the resistance gradient means a resistance per unit length. So what will be the resistance of the length OC? Kx, right? And similarly, the resistance of let's say CA will be K times 100 minus X, right?
Yes.
Now this entire circuit is basically a Wheatstone based circuit. Do you realize this? So this is O, this is A, this is B, this is C, and battery is connected here. So this is the equivalent circuit. You can convert like this. So this will become R. This will become S. What is this resistance?
K
X.
And this is K.
100 minus X.
So for balance condition, what is the rule?
R by Kx equal to
Just
S by.
yeah. So you can take this variation. R by S equals to Kx by K
K
100 minus x. So for balanced condition, you must write so for balanced condition, we can write R by S is kx upon k times 100 minus x. Okay.
Yeah.
And therefore the R turns out to be in the ratio of length. Because anyway, what matter is the ratio. So you can see now that the resistance which was unknown can be derived once we know the null point location. And this is the formula for the unknown resistance in terms of standard. Let's talk about the practicality, how it is done in lab. So in lab, generally the null point is, or you can see the point, the jockey is put near the center of the wire, the meter wire. Okay. And instead of moving the jockey, we change the S value. So as you approach close to R, the current in the galvanometer will decrease. And if you go away from the R, it will increase. Because by putting the C at the center, the Kx and K 100 minus x will be same. So the ratio is 1:1. So if this ratio is 1:1, if I choose x equals to 50, if I put x equals to 50, what will get? I'll get 1:1 ratio.
R is equal to.
Then the null point will be only obtained when R is equals to S.
Yeah.
So how it is actually done in the lab? The rule is we put the jockey at the midpoint and we keep on increasing S at a regular value. So let's say you increase the S from the present value by 5 ohm, and you see there is a reduction in the current in the galvanometer. It means you're going in the right direction. So you increase by next 5, and then what you see that when you increase by next 5, so instead of decreasing, it is increasing. So it means you're going in the wrong direction. So you will shorten your interval. So instead of 5, you will make a jump of 1 ohm. Then when you go from 5 ohm to 6 ohm, again you see it's decreasing. Then you go from 6 to 7, again you see decreasing. But even the moment you go to 8, it will increase. It means again the answer is between 7 and 8. So further you reduce the jump intervals. You make it let's say 0.1 ohm. And in that way, depending on the accuracy, you keep on shifting till you get it balanced. And if it is very close, if the current is really small, we assume balance condition is achieved, and then roughly this is the answer for the unknown resistance. Now the question is why midpoint is chosen in practical lab experiment. The answer is accuracy. So a null point near the center will give you the most accurate results mathematically, but the null point quite away from the center or close to O or close to A will give you less accurate answer. So let's try to investigate what is the meaning of accuracy. And for that, we need to do the error analysis. So calculation of error in R. Why calculation we need to do? So X is something you are measuring on the meter scale. So what is the least count of meter scale? What is the least count of meter scale? Now, least count means what is the smallest possible value that can be measured using meter scale?
Sir, it's 0.1 centimeter.
Hmm. And it is 1 millimeter.
Yeah.
Yes.
Now, if you have seen the meter scale, and let's say if the jockey is in between two such lines called the millimeter line, can we measure that value? So if the reading falls between two lines, which is having no calibration, I have just simply zoomed it. So if it is 1 millimeter, so one line is here, one line is here. If your reading turns out to be somewhere here, what we cannot measure? We cannot measure this value. Yes or no?
Yeah.
Because that is not calibrated. So what is the worst case scenario that we cannot measure? How much we cannot measure? If I move this arrow here, can we measure now? Yes or no?
No.
No. Can we measure now?
No.
No. Can we measure now? No.
No.
No. No. So what is the maximum value that we cannot measure?
1 millimeter.
1 millimeter.
1 millimeter.
So the least count is also called the maximum possible error of an instrument. Okay. So what is the least you can measure is also the most you can't measure. Just it's the idea of limit. So just left of the arrow line, left of let's call A and B. So just left of line B you cannot measure, but just right on B you can measure up to B, but again you cannot measure. So the worst case scenario that we cannot measure is the least count itself. So we call least count as also the maximum possible error of the instrument. So every instrument will have some error in its calculation, equivalent of its the least count. So when you perform the actual lab experiment, the answer of X we express as some number, maybe let's say 60 centimeter, plus minus, let's say point, it is less than 0.1 centimeter, right? So 0.05 centimeter. So this is what you can measure and this is what you cannot measure, or you can say this is the maximum possible error. So in case of meter scale, in case of meter scale, what is the least count here? One millimeter, which is 1/10 of a centimeter. Is this clear?
Yes.
Yes.
So this is also called error in X. So this is called delta X. Now, error calculation is all about finding the worst case scenario. That what is the worst you cannot measure? What is the worst you will have the error? What is the worst you will have the uncertainty? So the word error actually denotes the uncertainty in measurement. The other definition is maximum possible deviation, maximum possible deviation from its true value third point, error is always positive because we talk about deviation. It could be on the right, it could be on the left of a number. Deviation means the value by which you oscillate. And when it comes to the instrument, the error of an instrument is well defined by its least count. So error of an instrument is well defined by its least count. So once you know the least count, you know the error as well for a device, for an instrument. Okay. Now the question is how error is calculated. So let me teach you quickly about error. So so I'll teach you error analysis in detail later on, but right now we need to know a bit about error analysis. So first of all, we'll talk about what is measurement. What is the meaning of measurement, guys? How to define measurement? Any guess? Let's say you go to some grocery shop, the old Kirana store, not the new one. And you must have seen the weighing machine or the physical balance. Okay. So the moment you see the physical balance, you will see there are two pans and there is a rod connected to the pan. Pans are suspended from the end of the rod, right? And you lift the rod in the middle. On one of the pan, you put the stuff you're trying to buy. And on the other pan, what you put?
The measurement stones.
Yeah.
The weight, right?
Yes.
Yes.
So what is the meaning of measurement? What we are doing actually? What is the meaning of measurement?
So like estimating the amount which we need for something.
Measurement is an act of comparison between unknown and standard. Simple. So whenever you do some measurement, you compare against something standard. So 1 kg, 1 meter, 1 liter, everything is well defined in the Weights and Measures Bureau. And it was decided in the World Consortium of scientists, researchers across the world, which represent their country. They go to for a conference in France, Sevres. That conference happens every few years. And in that conference, they together decide that what should be the standard for the world. Okay. And why measurement, you can say, standardization is important. The reason is the entire purpose of development of science is for the trade and commerce. So when you trade between countries, there should be well-defined protocol that will decide the price of a commodity, and therefore the weights and measurements are very, very important. It creates a kind of uniformity across the world in terms of currency conversion, in terms of weight conversion, in terms of other things. Otherwise, everyone will pick some stone and will say it's 1 kg. So it's very difficult and chaotic to, order the world if everything is at the whim of a person or even the whim of a country. So the soul of measurement is science and commerce and trade, you can say. Also to exchange the scientific discoveries at the same scale, and standard is well defined. And therefore, when you use those well defined standards to make your own measurement, then you actually compare against those standards. That's why we say measurement is an act of comparison between unknown and standard. Okay, that's very simple definition. Definitely. So this is how measurement is done, and that's very interesting to know that why we need to define the standard kilogram or meter or something, because this definition will serve as a purpose to recreate the actual object from the definition. Otherwise, let's say there's a World War III and there is a nuke attack among various nations, and in that nuke attack, all those physical standard of weight and other things gets destroyed. So we want standard to be reproducible in case of calamity, any natural disaster, or in case of some nuke attack or any world war. Once we destroy the object, how to recreate it? Let's say if all of the notes which I am sharing with you, PDF, one day your entire phone crashes and you lose all of the PDF. So essentially, you will lose all of the information that you have learned so far. But then again, if we have some way to store somewhere else in terms of definition, if we have some textbook which is preserved somewhere, so that we can recreate the knowledge, print the knowledge, and distribute the knowledge. Now, those things are required to run the world as a whole, to run the global civilization. We need some standardization of not just knowledge, but everything. So that's why the weights and measures are so important. And we have the World Council for the same. We have a national council. So in India, who takes care of the weights and measures? Anyone knows? So in every country, there's something called National Physics Laboratory. So NPL is taking care of everything in India. It is in Delhi, New Delhi, in Pusa Road. I have seen that. Okay. So in India, NPL is the authority which takes care of the weights and measures. And then we have the subdivision. In every state, we have the weights and measure, you can say, lab, which locally takes care of these standard practices. Otherwise, people will do the corruption. They will create their own weight, and you can actually sue against these malpractices. They will put into jail. Okay, once you understand how. believe that it is doing some wrong practice. So the weights and measure is something really important, and there is a complete governing institution across country, state, district level, where people go and get their uh, commercial weights checked every year, and they obtain the certificate or license. Okay, anyway, so the measurement is an act of comparison between unknown and the standard. So what we compare against is called the true value sometimes. And true value is also called mean value. So what is the value of G? So the value of G is how much?
9 point.
9 point.
Let's say this is the value of G, 9.8 meter per second square, which is known to you. So when you perform the simple pendulum experiment in your lab and you obtain the value of G using the pendulum, so there you compare against this standard which is known to you, isn't it? And then you say that, okay, your reading is very accurate or very bad. So someone is getting 9.7, someone is getting 9.6 also, someone is getting 10 also. Okay, people also get 12 and 13 because they come from different planet. But nevertheless, you have something to compare against. But if we talk to Newton, in his era, the G was not known in its value. So when he performed the experiment, how you realize that this is the true value? Or this is the value that he needs to know? So he did the mean value calculation. Okay. So what he did, he performed an experiment, and he performed for sufficiently large number of times in a very controlled environment. And when he performed the experiment a large number of times in a controlled environment, he got values which was oscillating. So he took all values and then he simply took the mean of large number of repetitive experiment. And once he got a large number of readings, when he took the average, he got the value 9.81. And that is why he believed that this is the true value of G. Okay. But when you perform the experiment, you perform experiment 2-3 times. So in lab note, you must have read, if you get 3 concord reading, your experiment is successfully performed. So for the first person, you need to perform 1,000 times the same experiment. So that is why when people had the patience in the past and they used to perform the same experiment for the lifetime. Okay, imagine someone is doing the same job for almost 10 years, 20 years. Till he was convinced that this is the right answer. So in any experiment, we call something called trial. So you repeatedly perform the experiment, and then you get a value. Now this is value, this is not the true value. Okay, this is just a value. So let's say you're trying to measure some physical quantity, let's call it X. And in the first trial, you got the answer X1, but in the next trial, you got the answer X2, which may be same as X1, may be different. In the next trial, you got X3, next trial, you got X4, and then so on. In the nth trial, you got Xn. So what is the true value here? It is the average of all trial value. This is called the true value. Okay. Now, error is called deviation. In the language of physics, we call error as deviation. So deviation with respect to what? Deviation from the true value. So we were supposed to get this value, true value. And because we are finding the mean, we can also call true value as mean value. So this mean value, also called true value. Now, if you go back to your original trial value, x1, x2, x3, x4, x1 is may not be equals to xm. So there is a deviation, there is a difference. So when you subtract the experimental value from the mean value, you get some deviation, some difference. And this deviation is actually called error, but we'll come to that, what is exactly error. So first of all, we'll call just deviation, not error. Error will come later on. Just remove this. So what you get is deviation. Then you perform the next experiment. So you got this as a deviation. And you keep on repeating. Now deviation can be positive, can be negative because you're subtracting, right? So the x mean may be more than some value, maybe less than some value, maybe equals to some value. So we are particularly interested in the absolute deviation. Okay. So what is the absolute deviation? The modulus value. So what we do? We take the mod. Now the question is why we take the mod? Because we are
Error
looking
is
for
always positive.
because we are looking for the deviation from the true value. So deviation can be on the smaller side and can be on the bigger side, right?
Yeah.
So what really matter is deviation, the oscillation. So this is called absolute deviation. So what is error actually? So error is called mean of absolute deviation. Mean of absolute deviation. That's why I said error is always positive.
Positive.
So that's why error is also called mean absolute error. Mean absolute error or deviation. So you write, if you write x as the value, then delta x we write as error. Basically, we write delta xm, and here we write xm. So this is xm, this is the delta xm. But because we are lazy and because we are anyway engineers going to be, so because of this laziness, we drop the subscript to make the writing easier. Okay. So the mean absolute error we represent as mod of delta 1 plus mod of delta 2. Mod of delta n upon whole n. Okay. So this is, in a lab, when you actually perform the experiment, this is how we perform the experiment. And this is how we get the mean value, which is called true value. And we get the error value, which is called the mean absolute error. So these two things are clear.
Yes.
Now, error is not a significant terminology. Okay. Why it is not so significant? Let's try to understand this. So let's say you go and go to a grocery store again and you try to buy some sugar. So you order 5 kg sugar. Of course, there is a, let's say, you had some party at home and you need a lot of sugar to make some sweets. So in 5 kg, if the shopkeeper is giving you 10 gram less, will you mind much?
No.
In fact, on the physical balance, you won't be able to see a difference of 10 gram. Okay. So 10 gram, if I only look at 10 gram, then it is meaningless. That 10 gram is the error out of what value we are actually trying to measure. So you go to, let's say, a jeweler. So a jewelry shop. And there people don't buy jewelry in kilogram, right? Or they buy? Unless you're not some minister with lot of black money. So people buy gold jewelry in grams only, isn't it? Or in 5 kg. Do you order, okay, give me 1 kg of jewelry? Okay, you ask for a few grams. Okay, 10 gram, 5 gram, 20 gram, 30 gram, something in gram only. Now imagine you are going to buy a jewelry of 20 gram and the error is 3 gram. Will you mind it?
Yes.
You should mind. It's very expensive. So 3 gram is really huge quantity, because the overall quantity is 20 and 3 is a big part of it. So we define something more meaningful than error, and what we called relative error. So relative error is defined as error upon the true value. Like out of what? So this you can either represent as a fraction, or you can also represent as a percentage. So percentage. So we also have something called percentage error. So percentage error is basically a relative error expressed in percentage. So this is, and it is the percentage error which actually gives the right idea whether we should ignore such error or we should do the experiment again. So percentage is important. Let's say if the error is 2%. Okay. So in a context, 2% can be very big. In a context, 2% is very small. So if we are measuring, if we are weighing something and if the error is 2%, we may ignore. In a context, 2% we may not ignore. So if you know the context and if you know the relative error, then only you can judge or decide whether you should go with the experimental answer or evidence, or you should repeat the experiment. So error is actually less valuable in statistical analysis. Basically, the entire error thing is part of statistics. So relative error is basically more meaningful, and it will become even more meaningful if the context is known to us. Error is less meaningful. Okay. Now, if you go for a higher studies, you will study about, of course, right now you will also study in class 12th, something called variance. Have you heard the term variance? Which we represent by symbol sigma square.
Yes.
Sigma square called variance. Variance means variation, which is also like a deviation. But the variance and the absolute error differ in the way we express. So if you look at these terms, this is called deviation. And if you square each deviation, if you square each deviation and if you add, then this way of writing is called variation. And then we have something called standard deviation. Standard deviation. So what I have done is I have squared the deviation, right? So to get back the standard deviation, we must take the square root of the variance, right? So the variation or variance also represent square of error. Standard deviation also represents mean absolute error, kind of. But why we define in this particular way, there is some mathematical reason behind this. So modulus functions are not a good function in mathematics. Why? Because if you remember the mod of x function, if you plot it on a paper, it will look like this. So mod functions are non-differentiable function, right? These are non-differentiable.
Yes.
Yes.
And that is a big issue. Like if we have a corner in a mathematical graph, it becomes non-differentiable, right?
Yes.
Because differential means the ability to draw unique tangent. So if we have some corner, then how many tangent we can draw? We can draw infinite tangent, right?
Yes.
Like a seesaw. So because you fail to draw unique tangent, so you fail to have the unique derivative. So dy by dx becomes undefined here, isn't it?
Yeah.
Yes.
So every corner in a graphical manner we say is non-differentiable. And therefore, if a function is non-differentiable, can we do the maxima minima? No.
No.
So we cannot do the maxima minima. So when you will learn later on that a function, if I define the error, if I want to minimize the error in some complex situation, which you will learn, of course, if you try to learn about the machine learning and artificial intelligence, or maybe the advanced statistics. So there, the error in the output we want to minimize. But if I define the error in terms of mean absolute error, it is non-differentiable function. Therefore, we cannot, reduce it using some tool, mathematical tool. So that led to the discovery, or you can say the redefinition of variance. But the problem with the variance was the moment you define a variance, you disturb the dimension, right? Because when you square a physical quantity, the dimension will change. So to get back to the same dimension, what will do? You take the root. Okay. And that is how the birth of standard deviation took place. Okay. So we have something called normal distribution, which is very particular in nature. So we have something called normal distribution. So nature will always have some bell-shaped curve, and this is called the mean value. And then this is the deviation on both sides. So this is mu plus sigma, and this is called mu minus sigma. Okay. So if the sigma is really small, so that will help you in deciding that what kind of data or the experimental value is acceptable or not acceptable. So as you go deeper into the statistics, world of statistics, things will keep on, you will get new and newer definition. And many times you will see that a lot of definition can be interpreted easily if you know physics. Okay. So the mean value is like a center of mass. Do you know this? Okay. So in fact, the mathematical function of mean actually coincides with the definition of center of mass. So you know that how to find xcm, if you remember the formula x dm by x dm, or you can say x dA by dA. So if we have a graphical representation of a function, I can also find the mean value using the same center mass formula. Okay, so knowing physics helps in many ways. It is not just about physics. Even very complex mathematics gets some meaningful representation if someone really knows physics well. Okay. So this is the part of error, and let me complete this error definition so that you know error here itself. So although error is a separate chapter, but I'm finishing a part of here. Rest we'll do the calculation later on. So now you know the error, so what is measurement? So measurement is always expressed. So when you perform some experiment, and when you express your measurement so that your senior or your whatever you can say, professor or your guide, when you will put your result, then how to put the result? Okay, so you will say that measurement is true value, the value which you are sure of, plus minus means oscillation. So plus minus means don't add or subtract. It means It is the answer, and this is the uncertainty, the oscillation, the deviation, like this. So if we are measuring a physical quantity x, then x mean is called true value, and delta x mean is called error in the measurement. Okay, or you can say the uncertainty in the measurement, or something which you're not sure about. So you're sure about this value, but you don't know about this value. So this is a way to represent, and we are not supposed to add or subtract. This is just a way to say that the answer, I'm sure, is this, but this is the uncertainty. So the final result may oscillate from x m minus delta m up to. So because his result was oscillating in this range, so he expressed the answer this way. Okay. So x mean is called the true value, the mean value, and this is the error value. So mean, error. So how to interpret whatever is written beyond plus minus x on the right of plus minus x, that term is representing error, and what you write before plus minus is called the true value or the mean value. I hope this is clear to all of you.
Yes.
Okay, very. Now, if you are trying to, perform some experiment, okay, and let's say you're trying to find the length, okay. So for measuring the length, you will choose some instrument, right? Maybe a meter tape, a bigger one, the smaller one, a ruler, whatever. So when you are picking some instrument to perform the measurement of something, the instrument will have inherently some limitation, right? Or you can say it will have some least count. So least count is also called limitation. Yes or no?
Yes, sir.
And when a device will have limitation, then it will definitely have some error of measurement, because something it will never be able to measure. Okay. So when you put the tape against that, let's say you have a rod, you want to measure its length, you take a tape and you put against the rod, or you take the rod, put against the tape. It's the same thing. And you see where the edge is falling. If edge is falling between two lines where there is no demarcation, if your edge is falling here, then up to this point, your measurement is accurate. And this is called uncertainty. Do you realize this, what I'm saying? If the edge is falling here, then up to this value, I can always quote that this is the answer for sure.
Yes.
And this is the uncertainty. Yes or no?
Yes.
So measurement is the certainty plus minus uncertainty. Something which you are sure about and something you are confused about. Okay, what is that value? I don't know. And therefore, depending on the type of instrument, the error will change. Okay. So when you use the meter scale, the least count is 1 millimeter. But if you use vernier scale, which I will teach you later on in the error chapter, so in a vernier scale, it goes to 0.1 millimeter. And if you go to a screw gauge, it goes to 0.01 millimeter. So that is the accuracy up to which you can measure. And if you want to measure even smaller than that, you have to use the laser technique. Okay. And if you want to measure even less than that, you have to use the diffraction or interference idea. Okay. So these advanced technique to measure the dimension works on some indirect relationship of dimension and the various physical phenomena. Anyway, so we have something called propagation of error. So that's a very simple thing. You know that if you have performed some experiment and if it will have some error, which it will have for sure, any physical quantity which depends on that measurement will definitely incur the error. Yes or no?
Yes, sir.
Okay. So if you add, let's say, some sugar to water And if you add that water to milk, then the sweetness will also come in the milk. Yes or no? So
Yes.
if we perform some experiment and if that value which we have measured is used in measuring something else, then something else will also have the error, because error always propagate, right? So that is called the propagation of error. And what you need to know that if I have a quantity A, which I am representing as AM plus minus delta AM, and if I have quantity B, which I represent as BM plus minus delta BM, then a quantity C, which depends on the summation of A plus B. So this quantity C will also, we can represent it as CM plus minus delta CM. Then the question is, how much is CM and how much is delta CM? So the answer is simple. The CM we can calculate using the formula itself. So to get CM, what we do? AM plus BM. So adding the true value, because this is the dependent relation. So to get the true value, we use the dependent relation to get the true value of CM. Now the question is how to get the delta CM. Okay. So for delta CM, we add the, or we put the error of both terms. We add plus minus delta M plus minus delta B. Now the question is why we have written plus minus? Because error is the maximum of this, maximum positive value. So how to get the maximum? The worst case scenario. So maximum will be simply addition, isn't it? Do you realize what I'm saying?
Yeah.
Hello, hello, hello.
Yes.
Yes.
So we say that error of sum is sum of error. So when we have a two physical quantity being added, then the dependent quantity will have error equals to sum of error in each quantity. What about the difference? But error is always the maximum positive value. So what is the maximum positive value? So what you realize? Error is always positive. You know? We are still adding the error. Error means the worst case scenario. So even while taking the difference, the worst possible error that we can go through is the summation only. So error of sum or difference of two physical quantities is always sum of error. Understood?
Yes.
So whether you are adding or subtracting, the error will only get added. We never subtract error. Error means worst case scenario. The worst case means what is the worst we can have? Because if you are ready for the worst, then anything else will be better only. So while calculating the error, we always go for the worst case scenario. So we always add error. Errors are always added. We never subtract errors. Okay. So in addition or subtraction, the error is simple. You just add the error of each. You're done. The next one which you need to know is multiplication and division. So how error will propagate in case of multiplication? The moment we have multiplication or division, instead of absolute error, we try to calculate the relative error. So let's say we have a physical quantity Z, which depends on two quantity A and B like this. So if you try to write in detail, you can write AM plus minus delta AM. This is lengthy one, but later on you can just add BM plus minus delta BM. and you can keep on expanding AM, BM, plus minus AM delta BM plus minus BM delta AM plus minus delta AM delta BM. So if you try to expand, you will get something really bad like this. Just a moment.
Sir, you're on mute.
So we can write that this as AM BM plus minus AM delta BM plus minus BM delta AM. And when you take the product of two error which are very small in value, so product of small quantity we always ignore. So small into small is very small, right?
Yes.
So we'll keep up to here. And now the maximum of this will call the error, right?
Yeah.
So if you compare, what you'll get? Delta Zm is how much? Okay, first of all, what is Zm? It's very simple. Use the formula directly to get Zm. How to get the delta Zm? So maximum of that will be Am delta Bm plus Bm. Now this way of writing is not so nice. So what we write is a relative error, right? If you remember, this was the relative error.
Yeah.
So dividing by delta means dividing by Z means dividing by AM BM, right? So if you divide like this, what you get? So can we write this as delta BM by BM plus delta AM by M? And this is the lesson. In case of product, the relative error of the dependent quantity is sum of a relative error. So you add the relative error whenever you have something either multiplied or divided. Is this clear?
Yes.
Similarly, if I have Z equals to A square, then delta Z mean by Z mean will be, so A square we can write as A into A. Can we write like this? So here A and B both are same,
Yes.
right? Which means we can write as 2 times of delta M by M. So what you learn from here? The power gets multiplied in calculation of relative error. Is this clear?
Yes.
In case of division, the delta Z mean will also remain the same as for multiplication, because error is always the worst case scenario. So relative error always gets added, but the mean value will be A mean upon B. That's it. I hope this is clear. So in multiplication or division, what we do? We simply add the relative error. Is this clear?
Yes.
Yes.
So now last thing, if I write something Z power P equals to A power A, B power B, C power C, D power D. So this is essentially multiplication as well as division. So the mean value will be simple in calculation. Just put the mean of every value. But how to find the error? So as I said, power gets multiplied. So we're at P times delta Z mean by Z mean. the relative value is equals to A times. So keep on writing like this. You're done. And again, no need to worry about the sign. It is always going to be positive. I hope this is clear what I'm writing here.
Yes.
So relative error always gets added, and the power gets multiplied. So this is what you were supposed to know for this discussion to proceed. So can we proceed now?
Yes.
So, so here we have so for meter bridge, R turns out to be how much? So as per the rule of error analysis, standard is something which is without error. So anything which is standard or constant, we never calculate error for that, or you can say the error will be 0. So delta S here is, so for anything constant or standard, error is always 0. So if I write y equals to, let's say 10a, so do we have error in 10 or a or both?
A.
That's logical, I hope so.
Yes.
So 10 cannot have error. So if I write 10 in terms of some symbol, then symbol cannot have error also. Okay, I hope this is clear.
Yes.
So now R is variable, X is variable. So the way of writing is, this is the case of multiplication and division case.
Yes.
So R mean will be how much? X mean upon. Is this clear? And
Yes.
delta R mean upon R mean, the relative error in R will be how much? So we have two terms. X in the numerator, so we can write as delta X mean upon X mean plus delta 100 minus X mean X upon the error of the denominator upon. Now, how to find the difference of error? So difference of error is also sum of error.
Sum.
Error in difference is sum of error.
Yes.
But 100 is a constant, so it will have 0 contribution. So all contribution come from where?
Minus.
But error cannot be negative, na?
Yes.
See, error of difference is sum of error. So you add the error of this number and this number, correct? But this number will contribute 0.
Yeah.
So error in X is the answer. Do you realize this? What I'm saying? This is very important. So when you
Yes.
calculate the error in a difference of physical quantity, we don't subtract the error, we only add the error. Yes or no?
Yes.
Is this clear? Yes or no?
Yes.
Yes.
So you have almost finished the 50% of error chapter. So error chapter takes only one lecture to finish everything. So anyway, this will save my time. So the error is written like this, which I'll elaborate a bit. Can we take this as common?
Yes.
An error in measurement of length by the ruler will be equal to the least count. Yes or no?
Yeah.
How we measure the error in length? Using the meter scale, na?
Yeah. Yes.
And in meter scale, what is the error value? It is well defined.
Yeah.
So that must be equal to the least count of the device itself.
Yeah.
Now you tell me how to minimize the relative error. So we need to maximize the denominator actually.
Yeah.
Because numerator is fixed value. This is constant, this is constant, this is known to us. So how to maximize this value? If you know calculus, you can do it.
Differential.
So it will be only maximum when both terms are equal, right?
Yes.
So the minimum error occurs at 50 centimeters. This is the proof. Understood? So you may be asked this question in some examination. In meter bridge, the condition for minimum error is when x is 0, x is 100, x is 50, x is 75. What is the answer?
50.
So this is simple question that you will face in some random examination. Anyway, we got the error formula in general, and we proved the minimum case scenario. So to minimize the error, so this is the general error. And why I need to explain so much? Because this was JEE advanced problem. So please open your JEE 41 years or whatever, or a resonance sheet if you have. Have I shared the resonance sheet of current and electricity? I hope so.
No, sir, you had shared the assignment only.
Oh, just a moment. Let me share it. Okay, now I have shared. You can open it. Okay, I think it is. Yeah, it is the last question. Page 26, question number 18.
Yes.
Can you see the question? It's a JEE 2014.
Yes, sir.
And hopefully now you can solve. So try this one for some time, then I'll come back to you.
Hello.
Done, guys?
Yes, I got the answer.
Which one?
Option C.
Option C.
Yes.
That's the right answer.
Yes.
Anybody else getting the answer?
Yes.
Very good. So you can solve the next question, question number 14 below, page 28. Question number 14.
Okay, sir.
Sir, done 40.
Solve question number 12 of CBC 2009, page 30. Question number 12. And question number 9 also. From CBC. It's a board examination question.
Sir, after 14, which one do we have to solve?
14 is done, no?
Yeah.
So after 14, page 30, it's a board's question. 9 and 12. There's 14 also here. Then question number 23. Solve all these questions. You will have sufficient practice of meter bridge. All done?
Sir, last one.
Last.
Yes, sir. Yeah.
Very good. I hope it's done right. All done.
Yes.
So anyone would like to ask in doubt in this meter bridge?
No, got it.
Very good. So the
No, sir.
last concept in the meter bridge is called end correction. So usually in the meter bridge, we cannot put a 1 meter wire just like this. We need some connecting wires here, right? And we also need some connecting wire here. So the wire which you wrap something, or if you use some additional wire for a binding or connecting, that will also offer some resistance. Yes or no?
Yes.
So the total resistance of the left arm, the kx part, will be more than kx. And similarly, the total resistance of the right arm, that is k 100 minus x, will be more than k 100 minus x. Yes or no?
Yes, sir.
So this extra resistance in a practical scenario always comes into picture. But that extra resistance we add as a length equivalent of resistance wire. So what I'll write here, the resistance of connecting wire near the ends of meter wire also offers some resistance which we add as a length equivalent of meter wire to modify the result. Okay. So let's say the meter wire is 100 centimeter long with resistance 100 ohm. What is the resistance of per centimeter? 1 centimeter. If 100 centimeter is 100 ohm, so 1 centimeter is
1.
1 ohm.
1.
So let's say the left connecting wire offers 4 ohm and the right offers 3 ohm. So how much we need to add the length of wire on the left side? On the left, how much I will add? Earlier, the null point we obtained at x, so we used at kx. Now, because the null point is at x only, that's it. And the connecting wire on the left side is offering you 4 ohm resistance. So what is the length equivalent that we need to add? What is the net resistance of the left arm now? Am I audible?
Yes.
1 second.
Pardon? See, if your null point is somewhere here, whatever, if this is x, this is and if the connecting wire is offering you 4 ohm this side and connecting wire is offering you 3 ohm this side, this is connecting wire, and if let's say k is 1 ohm per centimeter, so to compensate for 4 ohm extra on the left, how much length we have to add mentally? What happened? Are you guys not getting what I'm saying? Definitely. See, x is the length, no? Okay.
Yes.
For the null point, I'm saying that the connecting wire here is offering you 4 ohm resistance. So how much length we have to increase to compensate for this 4 ohm extra?
4.
4 centimeter.
4 cm.
So the x must be replaced by x plus 4
Yeah.
Yes.
mentally. And this must be replaced by 100 minus x plus 3.
Plus 3.
Yes.
This is what I'm saying. Now it is clear?
Yes.
Yes.
Okay. Anyone is still not clear?
Clear.
All clear, guys? Tell me.
Yes.
So let L be the not L. Error in left arm. So this is the equivalent length of okay. So R by S, you earlier you should write kx upon, but we applied x plus epsilon L. That's it. So R turns out to how much? Add the end correction. That's it. So the question is how to know whether we have to use this formula or the previous formula. If they mention a connecting wire resistance, use the end correction. If they don't mention, don't use it. Simple.
Yes.
Yes.
So it's not a rocket science. And this was again a JEE advanced question, which is not in that booklet. You have to open the 41 years. Let me search. Okay, we are still left with one question, one instrument called potentiometer, and potentiometer will take at least 1 hour. So today I won't be able to finish, but in the next lecture, I'll finish the potentiometer and we'll start magnetism as well. Not magnetism. I think we can do conduction, or as you say, you want to learn magnetism right away or conduction first?
Magnetism.
Magnetism.
Yeah, so we'll go with magnetism because conduction is something which you can start reading and you will understand for sure.
Okay.
It's very easy because it is entirely based on concept of current and electricity up to conduction part. For radiation part, you have to understand the different theory which I will explain. So conduction is something which you can read from AC Verma and you will be able to solve almost 100% of AC Verma. Means conduction part only. Just a moment.
Excuse me, sir.
Yes.
So we won't be doing post office box in these instruments.
After this potentiometer.
Okay.
So it's a very small topic. It will take hardly 5 minutes.
Okay. Thank you, sir.
So, do we have 41 years?
Yes.
Can you search this in correction question?
Okay.
Okay, I am also searching. Okay, got it. Question number 31.
Which
Uh,
time?
2011. That should be in this booklet also. Yeah,
Yes, got.
Yes, sir.
yeah.
Yes.
That's very simple. Solve it. So they have directly given the interaction. Eh? So you can understand that meter bridge is really important from the point of view of JEE-Mains. So many questions. Figure is not shown. Okay,
It is
okay.
there.
No, it is there. Yeah.
It's there, sir.
Yeah. Yeah, you can do it easily. Not difficult. How much?
The answer is B.
Correct. 10.6.
Yes, sir. Even I'm getting.
Receive, you got the answer?
Yes.
I think this is pretty easy.
Yeah.
Tanish, you got the answer? Archit, you got the answer? No. I think not the answer. Shall I solve this or it's okay? It's done. Just one formula and you're done.
Yes.
Yes, sir.
Archit, Receive, Tanishi, Kanu.
Done, sir.
Have you guys solved this?
Yeah.
Okay. Do we need to solve this or shall we end today's lecture?
So from where should we practice current electricity now?
Current electricity, you have to practice from the assignment and the sheet which I have.
Okay. Okay.
And a resonance sheet actually. Yeah. Just
Yes.
finish the resonance sheet end to end, everything.
Okay.
From the start to finish, everything. That is more than sufficient. No need to solve anything else. And most of the JEE question I have taken care of. So you can revise it. But most of the JEE question we have solved in the lecture itself. So once you're done with the resonance, you are actually done with everything. Okay.
Thank you, sir.
Okay. Bye. Take care.
Thank you so much.
Bye,
Bye,
sir.
sir.
Thank you.